MEC cos omega CT plus MEC cos omega C plus omega MT plus cos omega C minus omega MT. Okay, so this is what you call the signal of the AM signal, where it composed of the carrier signal here, your upper sideband and lower sideband. So it means that for the AM signal, we have three signal here, where you have EC cos omega CT. So this is equal to your carrier signal. This is the next one is your upper sideband, where you have omega C plus omega M, and this one lower sideband is omega C minus omega. Because some of the people say, why omega? Because actually omega is related with the frequency 2 pi f here. So you can find f actually is equal to omega over 2 pi. So this is the frequency. Okay, right. Let's say we look in terms of the, it's not moving, eh? Okay, right? Okay, so you can see that total power, actually, if you want to add all together the power, is the total power actually is equal to your PC plus your PC plus P lower sideband plus P upper sideband. As you know that your power actually is equal to what? V square over, or maybe we can say that V peak over square root of 2. We take RMS value over R. So usually we take in terms of RMS value here. So we have V peak here over 2R here. Okay. So you can see that we all right. So we found out that here VC squared plus VLSB squared over R. So this one is a RMS value, actually is equal to V peak over square root of your 2 here. So after you do some manipulations, you can see that you square this, you add all together. At the end, you can find that you got EC squared over 2R plus M squared EC squared over 8R plus M squared EC squared over 8R. So we have power here in the carrier, upper sideband, maybe it's power in the lower sideband here. Therefore, the relationship between the total power transmitted and carrier power is as follows lah. So PT actually is equal to PC plus your PSB. PSB here actually is a combination of your upper sideband plus your lower sideband. Alright, so we have, and then if you look into our PSB, actually is these two. Okay, so PSB actually is equal to M square EC square over 8R plus M square EC square over 8R as well. So you got M square over EC square over 4R lah. Okay, so and then EC square over 2R is equal to PC. So that's why you add here. So you see that PC actually is to EC square over 2R. P upper sideband actually is M squared PC. So P sideband, lower sideband is actually P lower sideband plus P upper sideband plus here. So you got equal to M squared PC. So you can see that the total power transmitted is actually is equal to, all this is equal to 1 plus M squared over 2. M is your modulation index, PC is your carrier power. So this is how you can find the power in the AM signal. So it much depend on your PC here as well as the modulated signal here. The modulation index here. So what happen if your M is to 1? So if your M is to 1, so you have your total power actually is equal to 3 over 2 PC. Whatever PC that you have here, you just multiply by 3 over 2, you have PT here. Okay, for example, let's say you have your power here is actually is to 110 watt and your M actually is equal to 0.5 and M1 and M2 is equal to 1. This is just example. Okay, the total power transmitted for the AM signal actually is equal to your PC. PC is 10 watt. 1 plus M is 0.5 square over 2. So what is this value that you get now? So can you give me the answer? Can you give me the answer of this? PT actually is to 10 multiply 1 plus 0.5 over 2.
12.5.
0.2 square. Okay, sorry. This no. Okay, 1 plus 0.5 square over 2. So what's the answer that you get here? 1.25 watt. All right, so your total power now is 11.25 watt. What happens if M is equal to 1 here? P total actually is to 3 over 2 multiplied by 10 lah. So, what? 15 Is it right?
Yes.
50 watt So you see, your carrier now, okay, your carrier is actually 10 watt. If you have M tends to 1, so you can have the maximum power transmitted lah. So roughly about 15 watt. If your M is half, you see that your total power here is actually is less lah if you talk about your M is lower here. Because why? Because most of the power, as you can see from this AM signal, okay, it's coming from the carrier. So you see, so you have spectrum here. So this is lower sideband, this is upper sideband, this is your carrier. So most of the power is exists here because we know that PC is between EC square over R. Okay, all right, clear. So we know that the total power transmitted actually is equal to whatever PC that you have plus your sideband. So, but the problem is in AM signal, as you can see here, your EC square over 2R, there is no information actually. Okay, the information is only at the sideband because the information is coming from your M value, M value here. So, M is actually is equal to EM over EC. So, most of the power is here at M. So it means that the information is at the M here. So carrier, no information. So basically, if you are using the AM, you are wasting the power because, why? Because the power at this modulated signal for the carrier, actually there is no information. So that's why later on I show to you why we need to suppress here. So it means that instead of you are transmitting the 3 here, the signal here, okay, this is your full AM signal, so you can suppress it. So you just submit 2 sideband only. So this is called the double sideband suppressed carrier. So this is called the double sideband suppressed carrier. Okay, because of the information is the same, as you can see, the information is the same. So instead of you have this signal now, okay, okay, so this is what AM signal, full AM, where you have a carrier, FC plus FM, and FC minus FM. So this is upper sideband, this is a lower sideband, so this is a carrier. So the information is only at the lower sideband or upper sideband. So this is all the information. So what you can see here, you can suppress here, no trans. So you can see that you call the double sideband suppressed carrier. Okay, so you can waste the power. Okay, no need to have a high power because no information, right? So only the sideband that you are transmitting here, right? So but the bandwidth is the same. Bandwidth is still the same, actually is equal to 2 FM. No difference if you are transmitting full AM or if you are transmitting the double sideband suppressed carrier. Okay, all right. So next, so as you can see that power transmitted actually is a power AM is equal to PC 1 plus M square over 2S. So what we can see that since the information at the sideband, so we can actually calculate the efficiency of your system. The efficiency for the AM signal is equal to power in the sideband over power in transmitted power multiplied by 100%. Because the efficiency basically we relate with where is the information is. So the information is at the sideband, so only sideband can have the information. So we can take the sideband value here over your transmitted power, you multiply by 100%. Or if you can use it from the sideband, power in sideband actually is to PM square PC over 2, PC plus M square over 2 equal to M square 1 plus M square over 2. So you can see that this value actually is equal to M square over 2 plus M square. So the percentage of your efficiency okay, it depends on the value of your M here. So the highest efficiency that you can go is M is equal to 1. So that's why you have 1 over 3. Multiplied by 100%, so you have 33.2. So this is the highest efficiency for the AM signal. AM. Okay, so this is your. Okay, of course, if you use M less than 1, so the efficiency also will be less. Okay, so the average power sideband is about 50%, so PC is equal to PC over 2 here. It shows that PSB is dependent on the M signal. Okay, from M square over 2M square, from the efficiency, we see to M square over 2 plus the transmission efficiency is M is 1 only 33%. As I mean, therefore, we can conclude that the transmitted power signal is mostly carrier power signal contributing to 96.67. So as I mentioned to you, most of the power come from the carrier, but the carrier has no information. Okay, so that's why only 33% only in this particular AM signal. So in practice, information signal is a complex or non-periodic signal. It's about music, voice, image, etc. It consists of many frequencies and harmonic components. So it can be represented by this particular. So you can see that, and then in terms of spectrum, you can have in terms of that. Okay, right. So basically what you can see here, I just want to show you in terms of when you have the power in terms, if the signal is a complex signal, for example, you have a frequency from different frequency here. Okay, for example, you have the frequency of your F1, F2, F3, F4, and etc. Right? So for each frequency, okay, for example, you have VMT is equal to EM1 cos omega M1T plus EM2 cos omega M2T plus EM3 cos plus the. Let's say we have a complex signal here. Before this, we are talking about only here one signal frequency. But now, let's say, for example, we have a complex signal here where we have a lot of other frequencies. For example, we have omega M1, omega M2, omega M3, omega M4, and etc. Right? So as usual, if you want to find in terms of the VAM, T, same thing, you will see that EC plus B. So this is standard equations that we have, cos omega CT. So now instead of just a single frequency, now instead of have a single frequency, you have a complex frequency here. So the complex frequency, you can see that if you multiply just a normal multiplication, you can find out that M, you can represent M1 actually is equal to this M2, EM2, M3, and until M. So because for each individual here, we have the different modulation index here. Okay, so what we can see, we can write in terms of the power in AM signal actually is equal to PC1 plus M1 squared plus M2 squared plus dot until there. Okay, so it's the same thing. Okay, instead of you have one modulation index, we have a different modulation index, but we need to add all together the modulation index here. So, and then what we can see that is equal to PC1 plus M square effective over 2 here, where your M square effective actually is equal to M1 squared plus M2 squared plus dot. Okay, so but this one no, so M effective, so you have square. So M effective square is actually is equal to M1 square plus M2 square plus M3 square plus dot. Okay, so when you want to find just M effective, actually is equal to you just square root only. Okay, so this is what you call in terms of the signals that has complex frequency here. Okay, so if you draw the spectrum of this signal for the answer, you can find out. Okay, of course we have the carrier frequency, so you can see that you have FC like this, FC plus F1, FC plus F2, FC plus F3, and then the same thing as you have here as well. Okay, so FC minus F1, FC minus F2, FC minus. Okay, so this is a complex frequency from the, this is the spectrum frequency from the complex signal. So if you want to find what is the bandwidth, bandwidth actually is equal to upper here, okay, FC plus F3 minus FC minus F3. So we can find that is actually 2F3. So as a conclusion, you can find the bandwidth of this signal actually is equal to F3. It means that F3 is the F max. So this is the maximum frequency. If you want to find the bandwidth actually is equal to 2 multiplied by F max. Okay, all right. Ada soalan? Everybody is happy now? Okay, so this is in terms of the complex signal. All right, so you can see this is the carrier spectrum, FC. Of course, this one is FC plus F1, FC plus F2, FC plus F3, FC plus F4. Same thing as FC minus F1, FC minus F2, FC minus F3, FC minus F5. So if you want to find what is the bandwidth of here, so you can see that it's actually is equal to 2F4. F4 is the F max. F4 is equal to F max. So bandwidth is actually 2F max. Okay, so this is what we call the upper sideband, and this is the lower sideband. Ada soalan katanya? Everybody is understand?
Doktor,
Okay, what is it?
yang F max tu kita tentukan macam mana?
As I mentioned to you just now, F max is come from the maximum frequency.
Yang sebelah kanan.
Yes. Sebab yang ni sama lah. Sebab for example lah, kalau kamu adakan spektrum macam ni, okay, spektrum kamu kan banyak, kadang-kadang banyak kan, for example lah. So this is your F max. Okay, so if you do the modulated signal, you can see that dia akan dapat macam ni. So this is your carrier. So this one will be this one, and this one. So this is your FC plus F max. So actually is what? Is equal to 2F max here. Okay?
Okay.
Alright. Okay. So as I mentioned to you before, okay, so we also can see here as a summarize here, so we can see that the AM signal composed of what? AM signal what? Carrier plus sideband. Okay, you know, carrier plus sideband. So that means you have two sideband here. AM signal. So this one is where MEC is equal to. So this is the amplitude, and this is amplitude for the sideband, lower sideband and upper sideband. Okay, so this one is the same lah. If you talk about the same, but sometimes in the question you have to look. Sometimes they have upper sideband is 20 dB more than the single sideband, so it possible, so that you should know when you talk about that. So maybe 20 dB more, so you have to do some whatever from the log itself, so you can get whatever frequency that you want. So this is maybe some trick here. So FC, this is your carrier. So FC plus FM, FC minus FM. So this is the spectrum. So we can say that as a summary, AM signal consists of the carrier plus sideband. Okay. A carrier signal consists of apa? What is it? One carrier plus two sideband. And then the power for the AM signal, okay, what does it mean? The power in the AM signal is actually is equal to total power actually is equal to total power is in carrier plus power in the sideband. Okay, so sideband tu lah, upper sideband and lower sideband. Okay, so this and then the efficiency power sideband over P total maximum efficiency when M is to 1 is only 33%. So this is the maximum efficiency for the AM signal. Okay, what else? Bandwidth for the AM signal is actually 2F. If you talk about this, a single is tone. If F max, there is a lot of multiple tones there. Bandwidth actually is equal to 2 multiplied by F max. Okay, so this is the bandwidth for the AM signal. Okay, all right. So, okay, clear. Clear ke tak clear ke? Saya harap semua understand. Okay, so this is just an example. As we can see that here, AM session transmit power triangular voltage percentage is 6%. Get the average power of the carrier signal. Okay, so in this case, you want to find what is the AM. What is the average power? So average power inside your PC. So you can have in terms of PC, P total actually is to PC 1 plus M square over 2. So P total is given 10 kilowatt. M is given as 0.6. So if you do calculations, you find out PC actually is 8.47 kilowatt. Okay. Okay, all right. So there is another one I didn't show to you in terms of the what we call. This is in terms of power. We also can find in terms of currents. current from your current is the same thing as you have before from PT here. Okay, PT actually is equal to PC 1 plus M square over so 2. So this is the total power in AM signal. You also can relate with the total power. Okay, you can relate with the currents, with the total currents in your system actually. So where you can find out total current here actually is I is equal to I over IC. So from this equation as well, okay, you got it. You got it. From this equation, you just multiply P is to I square R P. So you just multiply is to I square R I total, and then after you do some simple calculations here, you can find that your what is your I total relates with your I carrier here. Okay, so and then after that you just put into these equations, into these values. Okay, so you get the results there. Calculate the modulation potential. So in this case, given I carrier is given, the root mean square current of antenna for AM section is equal to 8 ampere when only the carrier is transmitted. So this is I carrier, and then I transmit when this is the EM signal. So you know this, you know this one as well. Okay, from here the equations and calculate the modulation, so you can calculate this value. Okay, I just leave it to you to do it so that you can do it by yourself and see how is it. All right, so try to do it by yourself. Okay, the same thing for this one. You can see that I total actually, for example, calculate the antenna current for the motor signal when the pulse is down. You want to find calculate the antenna current for the modulated signal. So mean that after AM signal. Okay, so you want to find what is the current. So I total actually is so IC square root of 1 plus M square over 2. Okay, so you just put all the equations inside here. So you get the answer is 9.19. Okay, all right. Okay, next I want to show you in terms of double sideband. As I mentioned to you before, okay, as I mentioned to you before, we have in terms of a double sideband. So this is a full AM. Okay, so this is a full AM. Okay, so this is a full AM signal where we consist of two sideband and as well as a carrier. So this is your FC, this FC plus FM, upper sideband, FC minus FM. Okay, as we can see that here, you see that usually if you transmit the full AM here, you have a problems in terms of the power transmitter, because why? As I mentioned to you just now, at the carrier there is no information. Basically, if you transmit that together, you are transmitting the signal as well. You are transmitting the signal as well. So where you can see that, all right, here, okay, so you are transmitting the signal that there is no information. So what you have to do, okay, you can suppress it. So now you are transmitting only two sideband. So you have here, you have here. So you have FC plus FM, FC minus FM. So you have two sideband here. So this is called the double sideband suppress carrier. So that means because you suppress the carrier. So basically, if you use this system, you can what? You can save the power transmission for the AM signal. Okay, to increase transmitter efficiency, the carrier can be removed or suppressed from the AM signal. This produces a reduced carrier transmission or double sideband suppressor. A suppressed carrier amplitude motion scheme is 3 times more power efficient than the traditional double sideband with full carrier. So this one is actually is equal to AM lah, double sideband with full carrier. So what happened here? You have the information. Okay, you have a carrier frequency. You modulate it. Okay, so this is actually the signals that you will obtain from the output, and see. So you can see that maybe this information. But for the double sideband suppressed Crea later on, in terms of the modulations, you cannot use the simple diode detector. Okay, this one double sideband suppressed can need a complex demodulation process in order to get the information. Okay, right. So this is how we can find out in terms of, let's say we estimate as VMT is VM cos omega MT, VCT actually is equal to EC cos omega CT, where we found out that omega C is greater than omega M. And EC in this case we assume as equal to 1 here. V double sideband becomes equal to VMT cos omega CT. So you just they put like multipliers only here. So this is your VMT. So this is your VCT. VCT is equal to cos omega CT here. So if you have two signals, you multiply it together. So what you have, the output here is a VDSBSC here. Okay, so VDSBSC actually is equal to VMT multiplied by cos omega CT. Because you assume there's EC here is equal to 1, right? So VMT multiplied by. So if you have this value cos A, cos B, so how is it? You can find a half cos A plus B plus B. So this is a standard trigonometry that everybody should know lah. So V cos A, and then if you have cos A cos B plus minus. Okay, right. So VDSBSC VMT cos omega CT. So what we have here, EM cos omega MT cos omega CT plus EM over 2 cos omega CT. So this I think, okay, just look here. Okay, so let's say we want to find what your VDSBSC here actually is equal to VMT cos omega CT. VMT is VM is equal to cos, so you have EM cos omega MT cos omega CT here. So this is actually is equal to, this is equal to EM over 2 cos omega CT omega C minus omega MT plus omega C minus omega MT. Okay, so it's equal to that. So you can see that now they have a two spectrum here. Okay, so one is the omega FC plus FM, sorry, plus this one, FC minus F. Okay, so with the amplitude of your EM over 2. Okay, right. So frequency spectrum of AM signal actually is equal to, okay, this you can see that you have upper sideband and this is the upper sideband, so this is the lower sideband. Okay, so this is your FM here, FC minus FM. This one is what is it? This one FC is here, FC plus FM. Okay, so this is the upper sideband. This is the lower sideband. Okay, what we can see here, we have two spectrum here. Okay, for this is what called the double sideband suppressed carrier signal.
Doctor,
Yeah.
shouldn't the x-axis be omega?
What omega?
The
Oh, okay.
x-axis.
Sorry. If there is radian per second, so it's supposed to be omega. Okay. If I change to hertz, okay, so this one, all right? So it's the same thing. Okay, so if you talk about radian per second, so this is omega. If you talk about per seconds, only hertz, is 80 hertz. So if you have a frequency, so they will be in hertz, right? But in this case, as you can see that here, I show to you, so this is radian per second, this one should be omega, omega c minus omega m, omega c, omega m, okay? All right, so it doesn't matter, it's the same. Right, the only thing that this is angular frequency, but the only that we use usually in the spectrum, you look in terms of the frequency. Okay. Is everybody happy?
Yes, doctor.
Okay, no answer. Okay,
Yes,
only one.
happy doctor.
All right, okay, good.
Happy.
You happy here, you clap your hand.
Aku dah lain dah tu.
If
Aku
you
tadi
happy,
cakap.
you clap your hand.
Ini sebab mengantuk sangat lah tu. Okay, all right. So now we are going to look in terms of the power in double sideband suppressed carrier. Total power actually is equal to power in lower sideband plus power in upper sideband. So you add together here. So as usual, you take the value of your VRMS, you divide by R, you plus here. So you have in terms of EM square over 4R. Okay, so in double sideband suppressed carrier, all the power transmitted is sideband power. If you normalize in terms of 1 ohms here, so we have total power actually is equal to EM square over 4. Okay, so it's actually is equal to power in the sidebands. So this is a power in sideband. Okay, so we say that the efficiency is 100%. Why 100%? Because of all the power is being used and because all the information is in at the power itself. Okay, what happened if we look next? Next, we look in terms of single sideband now. Since you know that you reduce the power already from the full EM, you reduce the power, so it become double sideband separate. You suppress it. Now what happened? Because since you have two sideband that has the same equivalent informations, so you have this double sideband separate. This information is equal. P upper sideband is actually is equal to P lower sideband. Okay, the information is the same for both signal. So why you need to start to transmit this signal as well instead of you are having the same information. So what we can do, we can suppress one of the signals. We can suppress this. You can find out this is the single sideband suppress carrier or single sideband and only, or you can suppress here. You transmit the upper. So this also we known as a single sideband, right? So because you are transmitting the same power, so it means that if you transmit this signal, you transmit this signal, it doesn't matter because of the information is the same. So what you can do here, you see that you have the information here, okay, and this is your carrier. So of course you have the modulator here for the SSB. So you can see that if you multiply these two signal, okay, if we take considerations of BMT actually is equal to EM cos omega mt VCT actually is equal to EC cos omega CT. Okay, so you have VMT and VCT here. So if you have a multiplier, you just multiply it like modulator here. So you multiply VMT with the VCT. Okay, so you can find out this one is a VMT. Okay, so you find out this is the double sideband. So what happened here if you put some filtering process here? You filter the upper sideband, so you got the lower sideband. If you filter here, you filter the lower sideband, so you got the upper sideband. Okay, so this is another example how you can obtain the single sideband suppressed carrier. So you suppress one of the signal from the double sideband suppressed carrier. Okay, so what we can see here, both in AM double sideband full carrier, so that means the normal AM and the double sideband suppressed carrier, the transmission bandwidth is 2 times the modulating signal bandwidth. Okay, so we know that bandwidth actually is equal to 2FM or is equal to 2F max. Okay, for both AM double sideband full carrier or AM signal or AM double sideband subcarrier, both techniques transmit two sideband where we can say that this upper sideband and lower sideband which contain identical information here. So still you have the wastage of energy still open. Okay, another technique to reduce the error is the AMSSB, where you are going to transmit only one sideband by filtering, whether you want to filter the upper sideband or lower sideband. So it depends on your applications or at the frequency that you want from this lower side. So you see, so after you do some filtering process, you can see that you have the lower sideband and upper sideband. Of course, the upper sideband frequency, if you talk about higher frequency, the time domains here is becoming more shorter compared to the lower side. You cannot draw the same wavelength because we cannot differentiate between this time domain if you are drawing the same thing. Okay, if you want to analyze here, as usual, you put VMT is equal to EM cos omega MT, and VCT actually is the EC cos omega T, where we know that omega C should be greater than omega M as usual. Carrier frequency must be greater than informations. Sometimes I use word information. Okay, remember next week I will give you quiz again. Sometimes I'm using the modulating. So if I say in terms of the information, is the same thing as the modulating or sometimes just the baseband. Okay, this thing all same. Okay, baseband is a low frequency. Modulating also low frequency. The information is also low frequency. Okay, so let's say this is the example. VMT actually is to EM, VCT EC cos omega CT, right? So you have the signals here, VMT and VCT. So usually I just put some sort of like multiplier only. So here is a double sideband suppressed carrier signal. So what I need to do, I need to put the filter here. So filter, okay, if I filter the high frequency, I will get the lower sideband. If I filter the upper frequency, so sorry, I got the upper sideband. Okay, so we can see lower sideband actually is equal to EM over 2 cos omega C minus omega MT. This one is EM over 2 cos omega C plus omega MT. Okay, so you have two frequency here. lower sideband or upper sideband. It depends on the application. So this is just to show you what is the cos A, cos B. Actually, is cos A plus B plus cos A minus B. Sin A, sin B is the cos. What? What is the sin A, sin B here? Anybody knows? Can give me the answer? Kalau cos A, cos B, I usually put it there. What happen if I have sin A, sin B?
Instead of plus, it's minus.
Which one is a minus?
Minus 1 over 2 cos A plus B. The last one.
What? Half cos?
A
Cos what?
plus B.
A plus
Half
B
cos
is
A minus B, A minus B.
okay. A minus B, this one?
Minus.
Minus. Okay, this one? Plus. Okay? Right, so you have to make sure that you know the trigonometry. Yeah? So we have what? For a minute, we have cos A, cos B. Okay? We have sin A, sin B. We also sometimes we have what? Cos A, sin B, or sin A, cos B. Okay, so you should know this, okay, because you did on in the mathematics with the SPM level as well with the metric and so on. So you should know this trigonometry to solve the signals or the spectrum frequency. Because sometimes I just want to see whether you're understanding or not. I give you your informations now. VMT actually equals to what? EC sine omega mt, and then this one is VCT actually is equal to EC cos omega CT. Okay, so the only things that different maybe in terms of the phase, the rest is the same. Okay, the phase you have a positive or negative phase. Negative means 180 degrees, but if you talk about the magnitude, it will be the same later on. All right. Okay, so this is the spectrums of your SSB signal. So you have omega m, omega c, plus minus omega m, omega c plus omega m. Okay, so cannot be, so it means that if you want to draw this spectrum at the end, so you can see that you will have in terms of this one, or you have in terms of this one only. The rest, no. Okay, so this one will be omega c minus omega m, omega c plus omega. So this is what we call the single side band. Okay, all right. I think everybody is happy answer. And then if you talk about power, okay, if you talk about power in SSB signal, the same thing as we know before. Okay, so let's say I show you this is actually they took it from the AM signal. So from the idea of the AM signal before, we know that VAMT actually is equal to what? EC cos omega CT plus MEC over 2 cos omega C plus omega MT plus MEC over 2 cos omega C minus omega. So this is the AM signal. Okay, so if you look in terms of the spectrum, okay, so you have omega C here, omega C plus omega M, omega C minus omega M, which this one is EC, MEC over 2, MEC over 2. Okay, right. So now what happened now? Now we can see if you suppress one of this, okay, you suppress this, so it become like this, double sideband suppressed carrier. Okay, so we have omega C minus omega M, omega C, omega C. Okay, so you suppress this, you get double sideband suppressed carrier. If you suppress one of this, you have a single sideband suppressed carrier. So you cannot suppress all. If you suppress all, nothing can be transmitted. So you can suppress either lower sideband or you can suppress either upper sideband. So this is the things that you get from here. So if you look into the original signal, you can find out your single sideband suppressed carrier actually is m square over 4 multiplied by PC. So now you are reducing more power in transmissions your signal. Okay. If the signal is from multi AM signal, remember here I put here where the filter is being used to obtain the SSB, the output SSB is shown as here. Okay, this one I did from the AM signal. Remember, AM is not necessary AM signal. Okay, so what we have here, we have power transmitted actually is equal to power in the lower sideband actually is equal to power in the upper sideband. So what we have here, power in the lower sideband square over R into power sideband square, and then you square this one, you square as well. So you can see that here actually is equal to EM square over 8R. Therefore, you see, reduce the transmitting power by 50% compared to AMDSB SC. Because we instead of 100% just now, we reduce some of 50%. Therefore, power transmit is equal to EM square over 8 actually is equal to power in low sideband actually is equal to power in upper sideband. The efficiency is still 100%. So it means that SSB, DSB, the efficiency is 100%. Kalau ni is 33% for AM or DSB full carrier, DSB suppressed carrier. Okay, so we have efficiency is 100% for single sideband and double sideband. The only things that here is the bandwidth is getting bigger compared to the single sideband. Okay, so what is the bandwidth? What is the bandwidth transmission for the single sideband? Anybody knows what is the bandwidth of this? Bandwidth for SSB. Does anybody know what is the bandwidth? No response.
2F max as well? Or
Yeah, is equal to
2F max?
no, cannot. If you look in terms of the spectrum, right? So this is your FC, isn't it? Right?
Okay.
So this is your upper sideband, for example. What is it? FC plus FM. Right? So the bandwidth actually is equal to this. FC plus FM minus FC. So it's equal to FM. So the bandwidth actually is equal to FM or F max for the complex frequency. Alright, so we can see that AM we have bandwidth 2 FM, double sideband we have 2 FM, but for the single sideband we have 1 FM. So this is of course that is the advantage, more capacity, more channels that you can put in a certain bandwidth of the system. Okay, so this is in terms of a time domain for upper sideband, lower sideband, carrier, and AM signal here. So what you can see here, okay, so you can see that this is your carrier. Carrier, of course, is a high frequency. High frequency means you know, the times is very close, and this is your upper sideband, this is the lower sideband, and this is the AM signal. Okay, there is another one, the double sideband. The double sideband should be crossover. Okay, so you have like this. Cross, the signal will be cross. You can refer from my notes before. Okay, all right. Before we finish, I just want to the last one, and then we can try to have a look some questions maybe that you want to. And then we have another one is the vestigial sideband. Vestigial sideband is another signal where you transmit part of the sideband. So for example, if you have a full sideband like this, so this one is for the usually for the complex frequency. All right, so this is your F max, okay, FC plus, and this one is FC, this is FC minus F max. So in this case, what you have, vestigials mean part of this double sideband you are so you mean you like this, so you are transmitting like this. Okay, so this is part FC minus F1, F prime, F max, Fm. Okay, part. So maksudnya what we can see that this is part of the sideband. Not all, part only. So this is what we call the vestigial sideband. So because this is very important in the system that use a very wider bandwidth, like our TV systems. Our TV system is using about 5.5 megahertz. So if you are transmitting using both sideband, it's useless because of you need to have a higher bandwidth. So in order for you to reduce the bandwidth, you just have part of this. Because why? Because sometimes if you are just transmitting only this, sometimes the filtering process will filter this part of frequency. So what happen? Maybe some of the things, the information inside here cannot be captured. So in order to have both signal, so that's why they put in terms of very small bandwidth here so that it can be transmitting together. So it means that you have upper sideband and part of the lower sideband. Okay, so this is what we call the vestigial sideband. All right, so this is more on the equations that you can be used for the vestigial sideband here. As you can see that this is double sideband. The omega actually is equal to m omega plus omega c plus m omega, okay, plus m omega minus omega c here. So they just take part of this. Okay, the same thing of double sideband. Vestigial sideband actually is equal to vestigial sideband actually is equal to m omega plus omega c plus m omega c, so part of the carrier, plus m omega minus omega c with some value of your filtering here. So a special band pass, you see, filter having transfer function is used to suppress one sideband gradually and give the signal in a particular shape. So it means less expensive than SSB using lower filter. So this is part. So it means transmitting like this later on. So part of USB with the sum of the full USB with part of your LSB. Okay. All right. Okay. Next week I will try to do this one, generations of this DSB. Okay, because next week we have to finish this AM. Before the week after that, I'm going to, to give lectures on the FM because we are in a track now. Okay, right. So is there any question? Maybe I can have a look some questions here. This one also I'm not doing all, so some only. So if you have notes here, okay, for example, just this question from my notes. Okay, can you see question 1 here? 15 kilohertz. If you talk about 15 kilohertz, what is this frequency actually? Is it a carrier or the modulating signal or what?
Frequency.
Carrier.
Carrier. Okay. Is it carrier?
Yeah.
Carrier. But I put it here, carrier 500 kilohertz. How come that carrier? There is 2 carrier here. If you look this frequency, usually this is the information.
Oh.
This is the information. So this is the low frequency, or sometimes we call the modulating, because sometimes I didn't mention whether is it the modulating or information. So if you look in terms of 15 kilohertz sinusoidal signal having amplitude of 2 volt modulates here. So this is a carrier. Okay, so this is a carrier. So it's a 500 kilohertz carrier frequency having amplitude. So it means that it gave you like this lah. So you have VMT actually is equal to 2 cos omega MT here. VCT actually is equal to 3 cos omega CT. Omega here actually is a 2 pi, F here is 500K. This one is 2 pi, F is the 15K. Okay? Because this one is more on the generations, so it's better not for me to discuss yet. This is more on generation. Okay, if you have a books, maybe you can see tutorial 1 there. Okay? So make sure, that's why everybody need to have my book so that I can easily refer it. Okay? So can you see the question from my books here? Exercise 2. Exercise 2, where in this question it say that a carrier signal, okay, give in terms of signs here, VCT is a carrier signal, is equal to 3 sine 2 pi times 10 to the power 6 volt, has been modulated with the informations VMT 2 sine 2 pi times 10 to the power 3 volt to produce the AM signal. Assume the resistance at the transmitter AM is 1 ohm. Determine the signal equations of the AM. Okay, the question is asking you to find what is the modulated signal from this. Given VMT here actually is equal to 3 sine 2 pi times 10 to the power of 60. VCT here actually is equal to 2 sine 2 pi. Okay. Anybody can give me the answer? You can share me. Find the equation. Find the AM. The question is find the AM equations. If you cannot, if you don't want to write it, you can just say the answer. Should be okay.
So VC dengan VM tu terbalik.
What is the VC?
VC yang atas, VM kat bawah.
Okay, terbalik. Okay, correct. Okay, just the opposite VC sorry. Yang atas ni VC and VM. So now we want to find what is the equations. Anybody can give me the answer so that you can show it to me here. Share the slide. If you have already got the answer, okay, we can share the slide here. The question is the signal equation for the AM. So if you find this kind of question, what you have to do, you have to find out the standard equation for the what? For the AM signal. In this case, it doesn't matter whether it's a cos or sine. Okay, you just you just put the equations back towards the sine's value lah in this case. Nobody get the answer. Is there anybody want to show the answer?
Is this correct, Doctor? I showed my screen.
You show. Okay, I stop sharing. Okay. 2 sine. Okay, 2 sine. No. You cannot. You have to start with what we call the standard equation. The standard equation for the AM signal. This is not the AM signal. The AM signal should be, what is it? EC plus VMT, okay, multiplied by sines omega CT here. Okay, so this is a standard AM signal. Okay, so you have to change it to instead of cos, now you change to the, yeah, this is correct. But in this case, this is cos omega. You have to replace with the sine omega. That's it. So you cannot just do that. One is more on the double side bend. I cannot. So you have to make sure that you come up with the real equation, the same thing as this one. But the only thing that here is sine cos omega, you replace with a sine omega.
Okay.
Okay? So the rest will be the same. The rest will be the same. You have the EC, you know, VMT, you know as well. Cos sine omega CT, you know as well. All right? So you just put into that equation so you can find it, the answer.
So is EC equals to 3? Is EC equals to 3 for this question?
Yeah.
Okay.
Okay. All right. So and then after that you just do the manipulations, okay, based on the trigonometry as I mentioned to you before. So you will get all the informations. So that's why from the sign you have like a phase difference. The value is negative. All right. Okay. Okay, that's good. What is the next question? The rest in terms of the power or in terms of the others like sketch the AM waveform. So from these equations you can draw the waveforms. But the only things that you can see that the answer is given in terms of there is a negative value. So the negative value, it shows what? The phase, the reversal of phase. So it means that instead of a positive, you need to go negative. But if you draw in terms of the magnitude, okay, it's the same as before. Okay, right? The equations for the envelopes, okay? Of course, the equation of the envelope is from EC plus your what? VMT. That is the envelope, right? And then the last one is the power. Power, as usual, you know that EC square over 2R. Your PC, and then you got your equation. Okay, so your friends give you already the answer. VMT actually is equal to your EC plus VMT, okay, sine omega CT. So this is for the equation for the AM. Okay, so the spectrum, as you can see that the spectrum will be like this on one of them, because this is just the opposite, but you can still use the magnitude, you will get the same thing. Okay, and then the power in AM signal actually is to PC 1 plus M square over 2. M is actually is to EM over EC, the same thing. You got this value, and then you can solve this. All right. Okay, so this is one of the example. I think this is a final exam, maybe the example from the books here. Most of the question from the books is come from the final exam questions. Okay, all right. So, is there any question?
So, sir, it doesn't matter if it was in sine or cosine.
Yeah, it doesn't matter sine or
Just
cosine,
take the magnitude
but the
of the
problem
frequency,
is
right?
you have to make sure that your trigonometry is correct. Okay, the most important thing is your trigonometry. You cannot mix with a sine and then suddenly you have a different, the same as trigonometry as a cos. So on the end, the one is different. So you have to make sure that your trigonometry, cos A, cos B, Okay, sine A, sine B, or sometimes sine A cos B ataupun cos A sine B should be correct. Okay, because sometimes I can just give it to you, your information is in sine, but your carrier in cos. Okay, what happens? So of course, you have to have sine and cos as well, right? So make sure that you are having the same trigonometries that can solve your problems. Okay.
So, for example, if the carrier is in cosine, we need to change the other VM to cosine as well.
No, not necessary. It's okay. You can just use it cosine as well. If the carrier is a cosine and the information is sine, you can just use cos and sine because there is a trigonometry for sine and cos as well.
Oh, okay.
Okay, all right. Okay, so now time to have the what you call the what is it?
Attendance.
Attendance. That's right. We are not dealing with angle.
Difficult.
No, as long as you can understand the concept of this, should be no problem.
Okay.
Is there any more?